Hey guys, hope you're enjoying the first week of tutorials. I'm uploading this video because I wanted to kind of talk about some more basic ideas and statistics that will help you understand some of the lecture material. This is not a statistics course, and we basically don't expect you to really know a lot of this stuff in a lot of depth, but I think just for your own understanding of a lot of the stuff you're going to be seeing, it's good to just have a little bit of a refresher. Okay, so I don't have a very structured plan, but I want to start off by talking about random variables, and I guess the most simple random variable. So maybe I'll use a darker color. So really the goal for this video is to get to the point where I can talk to you about linear regression and the normality assumption, the Gaussian assumption that a lot of you were asking about. Okay, so we're going to start off from a really basic point. A random variable basically is a value that's random, right? The most simple random variable is called the Bernoulli p. Okay, and the Bernoulli p, you can think of it as a coin toss. Okay, so x can take on two values, 0 and 1, with probability 1 minus p, and takes value 1 with probability p. Okay, so what I'm saying is that x is a random variable. It can either be 1 or 0. Usually we think of 1 as a heads and 0 as a tail. You know, this is the idea of the coin toss. And if it's a fair coin, for example, so fair coin, then we have p just equal to 50-50, right? 1 over 2. Okay. So a random variable has a probability mass function. Okay, which is just basically the function probability x equals to little x some value. Okay, so we basically this is basically the probability mass function of the Bernoulli, because we either have the probability of x equals to 1 equals to p, and the probability that x equals to 0 equals to 1 minus p. Now we can summarize this information by writing probability of x equals to little x is equal to p to the power of x, 1 minus p to the power of 1 minus x, where x can be 0 or 1. Okay, so when x is equal to 0, okay, p to the power of 0 becomes 1, 1 minus p to the power of 1 minus 0 just becomes 1 minus p. So probability of x equals 0 is just 1 minus p. So we get this. And when x equals to 1, this term cancels out and we just get p. So I'm summarizing these two pieces of information into this one here. Okay. So this is the probability mass function. We also have the expectation. Okay. So the expectation of a random variable is the sum let me just write here in this fancy x the set of values that x can take. So x can take 0 or 1. So here we're going to be taking the sum over all the possible values that x can take of x px. Okay, and this is just another way of writing probability of big X equals to X, I'm just writing probability of little x. Actually, let's not confuse things. Let's just leave it as the notation that we're working like that. Okay, so what is the set x? Well, it's just 0 and 1. So this is just equal to the sum of 0 times probability of x equals 0 plus probability of 1 times the probability of x equals 1, which is just equal to the probability of x equals 1, which is equal to p. Okay, because this term is just 0, this term is just probability x equals 1, it's just p. And I may ask you, or you may get asked to find the expected value of x squared. Okay, well, this is just going to be the sum of x over all possible x's of x squared, probability of x equals to x. So in other words, the expectation is taking this term here and just plugging it into the sum. So in this case, it's going to be, again, 0 squared, probability of x equals 0, plus 1 squared, probability x equals to 1, which again is just equal to p. Okay, what if we just had a general function? Expected value of g of x. Well, again, it's going to be 0. It's going to be g of 0, probability x equals 0, plus g of 1, probability of x equals 1, which is equal to g of 0, 1 minus p, plus g of 1, p. Okay, so this is like just a general function, any function g, you can compute the expectation like this. Finally, we want the variance of x. Now you should remember from elementary statistics that the variance is the expectation of x squared minus the expectation of x, the whole thing squared. Okay, and we know that expectation of x squared, we computed it here, it's a p, and the expectation of x is p, so expectation of x squared is p squared. So this is equal to p, 1 minus p. Okay, so that's like kind of the most simple random variable, and this is a just to be really clear, this is called a discrete random variable. Okay, so it's discrete. Okay, discrete meaning that it can only take a countable number of values. So it could be, 0, 1, 2, 3, but it can't be like a real value, like a continuous distribution. Okay, all right, I think this is hopefully pretty clear. So let's look at another discrete distribution, the binomial distribution. With parameters. So the binomial basically is the number of successes in n trials, n independent trials. Each with probability p of success. Okay, so in other words, if xi is Bernoulli, I'm going to write Bernoulli p, so this is our coin toss from before, then if we toss the coin n times, okay, each toss is independent of the others, okay, and count the number of heads then this is a random variable called the binomial distribution with n. So it's got two parameters, n and p. Okay, so in other words, you can define b to be equal to the sum of the xi's, because the xi can either be 1 or 0, right? And the number of successes is going to be the number of ones, so it's just the sum over the xi's. Okay, so what is the probability mass function? The probability of x equals to x is equal to... Okay, well, let's think about it. If you, let's imagine that you did five coin tosses, and you saw the outcome 1, 1, 0, 1, 0. So this is a head, head, tail, head, tail. Okay, well, in this case, what is the probability of this happening? Okay, well, it's going to be p times 1 minus p times 1 minus p, right? Because they're independent, so you can just multiply the probabilities. So in other words, it's p to the power of 3, 1 minus p to the power of 2. So the exponents, because there's 5 total things that can happen, they have to sum up to 5. And 3 times we're getting a 1, so that's probability p, and 2 times we're getting a 0, which is a probability of 1 minus p. So the probability of x equals to little x is going to be, it's going to have this form. Now, this is the number of successes. So here we want x successes, so it's definitely going to be p to the power of x. And how many is left over? Well, we have, in this case, we got 2 here, it's because there was n trials. So this is going to be n minus x. Okay, so that's the main portion, but we have to be careful because let's go back to this 5 coin toss example. Okay, what is the probability that x equals to 3? Well, which outcomes give us 3 heads? Well, we know one of them, this one. But there's also another one, right? There's also this one, 1, 1, 1, 0, 0. There's also 0, 0, 1, 1, 1. There's 0, 1, 1, 1, 0. And there's a few ways of putting 3 successes in 5 trials. And the number of this is actually 5 choose 3. Okay, this notation, which is 5 factorial over 3 factorial times 2 factorial. So what goes here is a correction, right? Because if we just have this, then we're only looking at one of these guys. But we need to be careful, we need to account for all of them. So here we're going to have an n choose x correction. So there's going to be the probability of x equals x is going to be this times the probability. Okay, the correction times the probability term. Okay. Let's just ask a quick question. Before I use this notation to show the values that x, the random variable, can take, what are the values that can be taken now? Well, we could have a 0 value, we could have a 1, we could have 2, we could have all the way up to n successes, right? If I toss a coin n times, I can get 0 successes up to n successes. So this is a discrete random variable with these possible values. Okay. So what should we do now? Well, let's say that we wanted to find the expectation of x. And sorry, I know I changed the notation a little bit here. I used b for binomial. but we're just going to get into the habit of always talking about the current random variable. So here I'm talking about a binomial. Okay. So how do we take the expectation of this thing? Well, one way to do it is to go to the definition. X in script x of x times the probability of x equals to x. So this is equal to 0 times the probability of x equals to 0 plus 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 n times the probability of x equals to n. Okay, so this could be kind of a messy calculation. Another way to do it is to say, well, okay, the expected value of x is the expectation of the sum from 1 to n of Bernoulli coin tosses, right? Bernoulli random variables. Let me call them, sorry, I know it's terrible notation, but let me call it, I keep switching notation, where each yi is Bernoulli p, right? And hopefully you recall that expectation is linear, meaning that expectation of a plus b is equal to the expectation of a plus the expectation of b. This is always true. Even if a and b are independent or dependent, it doesn't matter. So this is the same as saying the expectation of I equals 1 to n, expectation of yi. And we know the expectation of yi from the previous slide is just p. So now we're summing up p n times, so we just get np. Okay, so the expectation of a binomial distribution is just n times p. And what about the variance? Okay, well, the variance is, again, let's use the same trick. The variance of I equals 1 to n of the Bernoulli random variables. Okay, now variance is not linear. Okay, so the variance of x plus y is not equal to variance of x plus variance of y in general. Okay, this is equal when x and y are independent. So in this case, the yi's are independent. So we can actually take the sum outside. So we get lucky this time. And we know the variance of yi from the previous slide. So this is just the sum of p, 1 minus p. So this is just equal to np, 1 minus p. And that's the variance of the binomial distribution, binomial random variable. Okay, cool. So hopefully that's making sense. What I want to talk about, though, is I want to go back to the Bernoulli. So imagine we toss a coin n times. And we don't know p. Okay, so this is a scenario where imagine you toss a coin. You don't know if it's a fair coin. It could be a biased coin, meaning it's an unfair coin. Okay, so the data is the samples x1, x2, x3, and let's say you observe xn, and we know that they're independent and identically distributed because they're all going to be Bernoulli p. We know a coin toss is Bernoulli p, but we don't know p. So the goal is to estimate p. So this is kind of where we start talking about doing statistics and estimation. So how do you estimate P? Okay, well, a very common technique, probably the most famous technique for estimation, is called the maximum likelihood estimate. And I'll just write this as MLE. Okay, so the idea is that you want to use the data, these are your data points, to come up with an estimator that estimates the true value P. Okay, because we don't know the true value P. Okay, so how do we do this? Well, we need to talk about a quantity called the likelihood, right? Because this is maximizing the likelihood. What is the likelihood? Okay, well, the likelihood is really simple. It's the joint probability of the sample. Okay? So we write the likelihood as a function of the thing we're trying to estimate, and it's just the joint probability, the probability of seeing the sample x1, x2, x3, xn. Okay, and just to be really clear, I'm going to write bar p just to make you guys realize that this is a function of p, right? Okay, now what do we know about this probability? How do we simplify this? Well, we know that if A and B are independent, right? Hopefully you remember that the probability of A and B is just equal to the probability of A times the probability of B, right? It's the same thing here. The probability of x1 and x2 and x3, well, if they're all independent, this is just going to be the product. I'm going to use this notation, the product of the probability of xi given P. Okay, well, what is the probability of xi given P? Well, each xi is a Bernoulli P, so this is going to be the product. Okay, what is a Bernoulli probability? It's P to the power of xi, 1 minus P to the power of 1 minus xi. So notice that these are actually dependent on the sample, right? And if I take the product, right? What is the product of these guys? Well, it's just P to the power of the sum of xi, 1 minus P to the power of n minus the sum xi. Okay, so all I did here is that, when you multiply 2 to the power of 3 times 2 to the power of 4, what happens? You just get 2 to the power of 3 plus 4, which is 2 to the power of 7. So when you take the product, all you do is you add the values at the top. And we can just simplify this using the notation that I like to use in the first video using the X bar notation. Okay, so now we have our likelihood, right? And here we want to take the maximum likelihood estimate. In other words, we pick, so what is MLE? MLE, pick P that maximizes the joint probability of the sample. Okay, that's all we're doing. We're saying this is the probability of the sample, okay? It's dependent on the parameter P. We want to pick the P that makes this probability as big as possible. Okay, that gives us the best estimate. All right, so the question is, how do we maximize this? Okay, well, there's a trick. And the trick is that you can actually work with something slightly easier Here, let me just write it here again. LP equals to P n x bar 1 minus P n minus n x bar. And we want to find the max. We want to maximize with respect to P of LP. Sorry, we want to find the argmax, and we're going to call this P hat. Okay, so this is the maximum likelihood estimator. It's the one that maximizes LP. Okay, well, it turns out that you can actually take, it's a very common trick to look at the log likelihood, and you'll see this a lot in machine learning. Okay, because the log is a monotonic function, so the P that maximizes log of LP is the same P that maximizes LP. And the reason we use this trick is because you'll see in a minute, so let me take the log likelihood is this fancy L, right? It's equal to the log of LP. Well, if I take the log of this guy, it becomes n x bar log P plus this guy comes down, n minus n x bar log 1 minus P. So this makes things easier because I want to take the maximum, right? So I have to take the derivative of this. It's easier to take a derivative of a sum than a product. Okay, so it's a very common trick. All right, well, we want to find the maximum. How do we find the maximum? Well, we use calculus. We differentiate. Okay, differentiate with respect to P. And okay, what is the derivative of log P? It's just 1 over P. So here we get n x bar 1 over P. And from here we'll get n minus x bar negative 1 over 1 minus P. And then we make this equal to 0 because we want to maximize. And I'll leave this to you, but if you do the algebra, you'll show that P is equal to x bar. And we'll call this P hat because it's the solution. But this is called the maximum likelihood estimate. So P hat MLE is equal to the sample average. Okay, which kind of makes sense because let's go back to the original example. We had x1, x2, xn. This is coming from a Bernoulli P. Okay. Well, let's say you don't know this, but let's say P is equal to half, right? Then how many of these n coin tosses would you expect to be heads? Well, you'd expect to see 50% of them, right? Half of them being heads. So then you would expect to see x bar, which is 1 over n times the sum of the xi's. Well, if 50% of these are 1, then x bar is just going to be half, right? If P is equal to 1, meaning that you'll never see any tails, then all of these guys are going to be 1, and x bar is going to be 1. So you can see how the maximum likelihood estimator makes quite a bit of sense in this case. Okay. Hopefully this is pretty clear to you guys. So now let's move on to something slightly harder. Okay, so we saw a couple of discrete distributions. Now I want to look at a continuous distribution. Okay, and the most famous continuous distribution is the normal distribution with mean mu and variance sigma squared. Okay, so what is this thing? First of all, now we have a probability density function. And basically a density function is like a mass function for continuous distributions. Okay, and the density function, we'll write it as f of little x is equal to 1 over root 2 pi sigma squared e to the power of negative 1 over 2 x minus mu, negative 1 over 2 sigma squared x minus mu squared. Okay, so what is this thing? Okay, well, basically it's just a bell-shaped curve. It's my best bell shape. It's centered at the mean, and the variance gives us an idea of the spread. Okay, so this could be mu plus sigma, mu minus sigma, mu plus 2 sigma, mu minus 2 sigma. The idea is that between two standard deviations, you'll see 95% of all the probability. Between one standard deviation, you'll see around 67%, I think. And then within 3 standard deviations, you'll see most of it. So I think 99% of the probability. Now, if you look at the functional form, okay, you'll see that this actually makes a lot of sense because if x is here, okay, this is the density of x, okay, it first takes the distance x minus mu, okay, and then it squares it, okay. So if x is really close to mu, if x is really close to mu, this is a very small value, right? But we want to give it a higher probability because points closer to the mean should have a higher density. Sorry, higher density, not probability. So what we do is we take the exponential of the negative of that. Okay, that's basically the idea. So I'm ignoring some of the constants, but the idea is basically that we want to give points that are closer a higher value. Okay, and that's why we take the so as x gets very far from mu, exponential of a negative number that's getting bigger gets smaller and smaller. Okay, so that's kind of the idea here. And this thing comes up all the time, so you pretty much memorize this eventually. I mean, you don't need to know it for this course off by heart, but it just comes up anywhere where you're doing machine learning or statistics. And well, the reason I want to talk about it is because I want to give you a harder example now, x1, x2, xn. Let's say we observe, but now I'm going to fix the variance. Okay, so the same problem as before. I see a sample of values x1 to xn. They're independently and identically distributed according to a normal distribution. We know that the variance is 1. Somehow we already know that. But we want to estimate the mean. Okay, so we want the maximum likelihood estimate of mu. Okay, so how do we do that? Well, let's just use exactly the same approach. We first construct the likelihood of mu, which again is the joint probability, or the joint density in this case. So let me just say, the density, this is not a probability function, right? So if I take f of 1, this is not equal to the probability of x equals to 1, right? Because this is a continuous distribution, so the probability that x equals 1, the probability that x equals to little x is equal to 0 for all x, right? Continuous distributions always have this property. The density at a point, okay, is kind of like just basically this value here. So you can compute probability ranges by looking at the difference between them. The probability is basically this area here. So the area under a single point, right, is just 0. There's no area. That's why we get this behavior. So density is not equal to probability, exactly. Anyway, so back to this. What I'm saying here is the likelihood of mu is the joint density, and we talked about independence already, so I'm going to skip a step and just write this. Okay, so this is the density of each xi, and we're going to multiply them all together. And let's write out the actual functional form. Let me just use this notation, 2 pi negative 1 over 2. So sigma squared is 1, so we get rid of the sigma squared there. E to the power of negative 1 over 2 xi minus mu squared. Okay. And if we just simplify a little bit, well, the 2 pi to the power of negative 1 over 2 becomes 2 pi to the power of negative n over 2. And the exponent becomes negative 1 over 2 times the sum xi minus mu squared. Okay, and what is the goal? The goal is to maximize the likelihood. So we want to find the argument that maximizes the likelihood. Well, if you look at this problem, okay, you can take the logs, but you can even just notice very easily that this term here doesn't make a difference because it doesn't have any mu's in it, so you can get rid of that. So this is equivalent to the argmax of the second term. And if we want to maximize this expression, well, this is an exponential of a negative value, so this is the same as taking the arg min of the sum of xi minus mu squared. Hopefully you can see that, because as this value here gets bigger, right, this thing gets, the exponential of that thing gets smaller. So if we want to maximize this value, it's like minimizing this number here. So it's the same thing. Okay? And if you do the calculus, so if you set up f of mu equals to this function, and then you take derivatives and make it equal to 0, you'll get that mu MLE is also equal to x bar. Okay, so please do this exercise in your own time, but just show that mu hat is equal to x bar. Okay, and that kind of makes sense because let me just erase that. If you think about the what we're saying, just imagine that mu is equal to 1. Okay? Imagine the true mu is equal to 1. So you're going to have your Gaussian distribution here like this. This is mu equals to 1. But let's say you have another Gaussian distribution here, which is centered at 3. Okay? And, well, if the true value is 1, a lot of your data is going to be, a lot of your xi's, like let's say x1, is going to be here. And maybe your x2 is going to be here. Okay, you're going to see a lot of values like this, maybe a value here, maybe a value even up here, a value here, a value here. Okay? Now, if I compute the likelihood L under the value 3, okay, hopefully you should see that, if I try to assume that the red distribution is my actual model, it should give me a worse score, right? A worse value than choosing the blue. So we want the likelihood, and I'm using the notation likelihood here. Okay, we should hope that this likelihood is less than the likelihood of the true model, L1. Okay, so this is the idea behind maximum likelihood, right? We choose the model that gives us the highest probability of actually seeing those data points. Obviously, under the model u equals 1, you're going to get a higher probability of seeing these points. So again, the maximum likelihood estimator mu equals to x bar makes a lot of sense because it's the center of the data points. Okay, so that should give you a distribution that is likely generated your data. Okay. All right, so what is the point of talking about all this stuff? Okay, so in the tutorial video, let's talk about linear regression now. In the tutorial video, I like to think of this as having, as kind of there being two approaches to talking about linear regression. Approach one, okay, is the kind of the optimization version. And approach two is the statistics version. Okay, what is the optimization version? Well, it's the version that we saw in the tutorial when we talked about, you know, you have your data, xi, yi. You have your model. So the model is that y hat I equals to beta 0, sorry, it's equal to a plus b xi. Okay, and then we estimate a and b by looking at a, b hat equals to the argmax, sorry, the argmin of the loss function 1 over n yi minus y hat I squared. Right? This is what we focused on in the tutorial. We derived this. We talked about it for a while. We talked about the multivariate version. You know, we've already covered approach one. Why do I call this optimization version, not the statistics version? Because there's no mention of statistics whatsoever, right? We just talked about a model. We picked a model. This is the model. We notice the model has some parameters, A, B. We set up a minimization or maximization, an optimization, and we solve the optimization, and we get some values, okay? This gives us, remember from last week, sorry, from this week rather, we get A hat equals to y bar minus B hat x bar, and B hat equals to x y bar minus x bar y bar, x squared bar minus x bar squared. Okay, so what is the statistics version? The statistics version is kind of a more advanced version, okay? Because it requires more assumptions and it gives us more things to work with. But basically the idea is that, so now let's talk about the statistics version. Okay, the statistics version says that yi equals to a plus b xi, okay, plus some noise, epsilon I. Okay, and the idea is that, you know, your data is going to be generated like this. The blue line is the true line, but there's always going to be some noise. So this is the error term, and this is kind of the what would you call this? You would call this the maybe it's not the best term, but maybe the trend, or the, you know, whatever. This is the true value, but the true value is always corrupted by some noise. You're always going to have some noise. So you can just think about it as, imagine that you're taking temperature on different days. You know, this might be the true temperature. You might have a good model for the temperature, but your measuring instrument, your thermometer, might have some error. So you're always going to get some kind of noisy noisy estimate of the truth. Okay? Then we need to make an assumption about the error. Okay? Well, the assumption that's very commonly made is that the error is a normally distributed random variable with mean sigma squared. Okay, that's just a very common assumption because the Gaussian distribution is very easy to work with. It's kind of a convenient function because all we're saying is that the errors, okay, the error is symmetric, right? Because remember, what does this look like? The error variable, right, is just going to be symmetric at 0. So we expect 0 error, but if there is an error, it's symmetric around 0. Okay. And that's kind of the setup of the statistical version of linear regression. Okay, but this kind of has a big implication. Okay, and let me just say one more thing. Xi is fixed. So in this version, I assume Xi is just a number. It's a constant. Yes, it's coming from the data, but it's just a fixed value. Okay, so what is this actually telling us? Well, it's telling us that hopefully I should have mentioned this earlier, but let me just write it here. If Z is normal with mean, mu, and variance sigma squared, then Z plus a number is normal mu plus that number sigma squared. So all I'm saying is that when you add a constant to a normal distribution, all you're doing is shifting it to the right. And similarly, if you do Z minus A, you're shifting it to the left. Okay, so let's go back to here. If I make this assumption about the errors, okay, what does it say about my Y's? Well, Yi is going to be distributed, well, this is a normal random variable plus a constant, right? This is a constant. So it's going to be normal A plus B xi sigma squared. Right? So you would have seen one of these two methods. You can either make the assumption about the error is normally distributed with mean 0 sigma squared, or you can assume that Yi is this. They're both the same assumption. And the reason is if I add a constant number to a normal 0 sigma squared, all I'm going to be doing is shifting the normal from 0 to this A plus B xi. Okay? Now, how do we estimate, right? How do we estimate A and B? Okay, well, we looked at the optimization way, right? This way up here. But we don't want to talk about purely optimization. We want to talk about statistics. Well, what did we learn about statistics just now? Well, given y1, y2, yn, they're all coming from they're all independent. That's really important to assume, and they're all coming from a normal distribution with a plus, each one has its own xi. So they're not, some people say this is identically distributed. I personally don't like that because identical means they have the same mean and variance. Here, each one has its own mean because each one has its own xi, but they are independent. So how do we estimate A and B? Well, how do we estimate any parameter for a statistical problem? Maximum likelihood, of course. So what is the likelihood? Now we have two parameters, A and B. Well, it's the product of the probability of the density. Okay, and I can write given AB here just to make it really clear. And this is going to be the product. Okay, let's just be really careful here. Remember what the normal distribution formula is, the density of the normal distribution, and let's just plug it in. It's 2 pi sigma squared, right, to the power of -1/2 times the exponent of -1/2 sigma squared times yi minus the mean, a minus bxi squared. Okay? And this is equal to 2 pi. So this is exactly the same problem that we just did before, right? You should see that the only thing that changes really is that the mean is a plus bxi, and we also have the sigma squared term here, okay? But basically everything else is the same, so there's going to be the exponent of minus 1 over 2 sigma squared times the sum I equals 1 to n, yi minus a minus bxi squared, the whole thing. Okay. Let me just rub this part out. Now, hopefully you should see that argmax, so argmax mu, AB of LAB is equal to the, well, okay, remember this term doesn't do anything because it doesn't have A and B inside. This term has A, B inside, and remember the exponent of the negative of this, if we want to maximize that, it's equal to the argmin of the sum yi minus a minus bxi squared. Okay, so hopefully you should see this problem is very similar to something we've already done. Up here, right? This is just the least squares problem. It's the same problem. So in this case, the MLE parameters are going to be exactly the same as the least squares parameters. Okay? It's really important that you see this. This is just the sum of squared values, right? And this is exactly the same optimization. Now, this is not always true. The maximum likelihood estimate is not, in general, going to give you the same result as the least squares estimator. It just so happens to be in the Gaussian case that because the Gaussian distribution is dependent on the sum of squares, just by the way we constructed it, that it actually does give you the same result. Okay, this is not generally true. It's just true in this case. I think this is actually the reason for a lot of confusion when you first see this, because you see the maximum likelihood, you see the least squares estimators, they're the same value. It's really confusing to kind of understand, is there really two different things, or is it the same thing with different terminology? It's two different approaches, okay? Remember, here in the first approach, right, we made no assumption about the yi. We didn't say it's Gaussian, we didn't say it's anything. We just said this is the form of the function, it's a linear function. And we just fit it with a loss function, and we did optimization, and we got some values. Here we made a completely different assumption. Here we're saying that the error is Gaussian. We do maximum likelihood. We just end up getting the same answer. Okay? So two different approaches give you the same answer. All right, so that's quite nice because we don't have to do much more math. Okay, so let's just, at this point, I just want to try to visualize what we're trying to do. So again, let me just write up the assumption. Okay, so what is this? This is mu I, and mu I is just equal to, a plus bxi. Okay, so you need to know the x. That's why I put this conditional on xi in order to actually know what the distribution is. Now, even though every yi has a different mu I, right, because they all have different xi's, they all depend on a and b. They all depend on the same a, b. Okay, so let's try to visualize what's actually going on. So here's my x-axis, here's my y-axis, and basically what we're saying is that there's some true line okay, and let me call this y equals to alpha plus beta x, where alpha, beta are the true parameters. Okay, we don't know what these true parameters are. We just assume that there is some true regression line out there. Okay, now let's look at xi. Okay, well, at this point, we just look at all the y values for this point. Now, what the true line says that the mean, right? We have a distribution of the yi given the xi, which is going to be Gaussian. Okay, let's just imagine that this is exactly the mean. So I know my drawing is not very great, but this is exactly the mean. Okay, and let me also draw the points that we actually observe. Okay, so green is actual observed data. Blue is the true line. And then using least squares, right, or using maximum likelihood estimation, I'm going to get estimates. A and B are the estimated parameters. Okay, and let me pick a different color. Okay, the estimated line might look like something like this. Okay, so this is y hat equals to a plus b x. Okay, so you see that the pink line or the purple line is based on the observed data. It doesn't necessarily have to be the same as the true line, right? Because, you know, ours is based on real data, and, you know, the real data might not give us a perfect picture of what the true line is. But the idea is to try to get a decent looking estimate, okay? And basically, we're just saying that each yi, okay, is going to be distributed along this line, okay, according to this distribution. The center of it is going to be the true mean, and the spread is going to be sigma squared. So the spread here is kind of the error, right? Sigma, well, it's just going to be sigma. So the standard deviation in each direction. And basically, you can think of this, right, because the assumption at the start was the epsilon I is normal 0 sigma squared. So what we're saying is that we have the true line, but the values are random, and there's an error around the true line, and the variance of the error is sigma squared. So this kind of, this is the width of this normal distribution is measured in terms of the standard deviation. Okay, so I mean, it's kind of a hard picture to, because there's a lot of things going on, but basically at each xi, we have this picture going on. So the true line always has the true mean, right, on here, and the regression line is trying to estimate that. Okay. Now, just note that even though the true line is blue, the observed value is the green. So how come? Well, because again, we have randomness, right? You're not just going to keep observing points on the line. You're going to observe, like for this particular xi value, the value that you observe can be any value under the red curve. It's most likely to be under here, like closer to the mean, because that's the highest probability. But it wouldn't be too crazy if we saw a point here, right? That's possible. That's definitely possible. Even though it's a lower probability of happening, it is possible. So the idea of least squares is to find for each xi value basically the mean of the Gaussian distribution, as long as all the means sit on a straight line, a plus bx. That's kind of the idea. Okay, so hopefully this kind of helps understanding that picture. Now let me go back and talk about approach 1 and approach 2. So this was the optimization approach, and this was the statistical approach. And we showed that the A hat, B hat, A hat, B hat, and we call these least squares. So I'll just put an LS here just to make sure that you know what type of estimator they are. And the B hat, A hat, MLE, right? They're both equal to the same thing. Let's just call it A hat, B hat, which is equal to Y bar minus B hat X bar and X Y bar minus X bar Y bar X squared bar minus X bar squared, right? So one might ask, what is the point? What's the point of A2, right? What's the point of approach 2? Well, the point of A2 is that you might want to understand how good your estimator is, okay? You might want to try to figure out what the expected value of the estimator is. What is the bias of the estimator? What's the variance of the estimator? These are terms that are going to come up a lot in machine learning. And basically, A2 gives us a way of answering these, whereas A1 doesn't give us a way to answer this. So under A1, the estimators, A hat, B hat, you kind of get these values, and then you don't really know much about X and Y because you haven't made any assumptions, right? So these are just numbers. They seem to work. They solve the optimization, but you don't really go further than that. So we can't answer questions of bias, variance, etc. Okay, and there's more important questions in statistics to deal with significance and things like this that we don't cover in this course. But that's the idea. The idea is that once you have the optimization approach, it doesn't really give you more in terms of saying things about the estimators. Okay, under A2, then you can answer all these questions. Okay, bias. So what is bias? The bias of any estimator, theta hat, is the difference between the expected value of the estimator minus the true estimator. Okay, So that's the bias. So the point of this is trying to measure the difference, like this is the true parameter, the thing you're trying to estimate, and you would expect that on average, your expected value of your estimator should come close to the true theta. So this value should be quite small, right, for a good estimator. Okay, so how do you compute this value for the A1 estimator, right, for the optimization estimator? It's very difficult because we don't have any assumptions on these guys. But under A2, okay, let's try it out. So let's compute bias of, let's start off with B hat, MLE. Okay, well, it's equal to the expectation of B hat. I'm just going to write B hat to save myself some time, minus the true parameter, which we called beta. Okay? Now, sorry, I didn't call it beta, I call it B. Okay, so the true value is B, because remember what we assumed yi is, or yi given xi is A plus B xi sigma squared, right? This is an assumption. These are the true values A and B, and we have an estimator B hat. Okay, so what is the expected value of B hat? Well, to do that, we need to plug in the value of B hat. Okay. Now this looks kind of scary, but it's actually very simple. Remember what our assumption on x is. Okay. X is fixed. Okay, and remember if we take the expectation of a constant, say 2 times a random variable z, okay, the constant can just come out to expectation of z. So here, everything to do with an x is constant. Okay? So we can actually take out this whole denominator outside of the expectation. Okay? And then what we have inside, well, this is a linear term, right? Expectation is linear. So it's the expectation of x, y bar minus the expectation of y bar. And actually, we can take x bar outside because x, again, is a constant. Okay, so let me just do it on the side here. Let's start off with the expectation of y bar, right? Well, why is y not a constant? Well, because it's a random thing, right? We assumed it's a random variable, so we can't just take it outside of the expectation. So what is the expectation of y bar? Well, it's it's the expectation of 1 over n times the sum of the yi's. This is the sample average. Okay, and 1 over n is a constant, and because of the linearity, we can take it inside of the sum. Okay, and this is 1 over n times, well, expectation of yi is a plus bi. A plus b xi. Okay, that's the assumption here. And if you just do some quick calculations, like the a comes outside, right? And then we have n of them, and then the b can come outside, and then we take the sample average, then we take the sum over xi's. So this is just a plus b x bar. Okay, so that's the expectation of y bar. Now, what about the expectation of x, y bar? Okay, let me do that on a different slide. Okay, the expectation of x, y bar. Okay, it's going to be very similar. But now we have xi, yi. Okay, again, the expectation, because xi is constant, can just go all the way inside. To here. And this is equal to 1 over n xi a plus b xi. And then this is going to basically be a x bar plus b x squared bar. Okay, so let's go back to the original thing that we were trying to do. We wanted the expectation of b hat minus b, and we showed that this, from this point here, is 1 over x squared bar minus x bar squared times the expectation of xy bar minus x bar times the expectation of y bar, which is just a plus b x bar. Okay, now hopefully you see that, and minus b. And hopefully you see that this ax bar and this ax bar are going to cancel out. And this is going to be equal to 1 over x squared bar minus x bar squared b. Now I'm going to take the b common, but we get b x squared bar minus x bar squared minus b. And now hopefully you see that this term and this term cancel out. We just get b minus b, which is equal to 0. Okay, so this tells us that the bias of b hat is equal to 0. Okay, so in other words, b hat, you might also hear that b hat is unbiased. Now, this is a pretty important concept, and if we just stuck to A1, we would have got the same estimator, but we wouldn't have been able to do more analysis on that estimator, and specifically we wouldn't be able to find the bias and talk about the variance, etc. Okay, now you can show, I'll leave it as an exercise, a very simple exercise hopefully, that A hat is unbiased. Okay, so the least squares, estimators, and the maximum, I mean, they're the same estimator. They're actually unbiased estimators. Okay, that means that the expectation of the estimator is the true value, AB. So the question is, does this work for multivariate? Multivariate regression. Okay, well, remember multivariate regression in approach 1, right? It was just the same optimization problem, but a different model. And it turns out that here, we're actually going to have the same approach 2. We're going to assume that yi given xi is normally distributed with mean mu I sigma squared I. Oh, sorry. It's just mu I sigma squared. And mu I, okay, now it's not going to just be I'm gonna go back to the W notation. It's not just gonna be W0 plus W1 xi1, right? Because now we have xi is now a vector, right? Because we have multivariate progression. It's going to be plus W2 xi2 plus 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 up to WP. And we usually write this as W transpose X I. Okay, and the distribution here is exactly the same, right? It's still going to be 1 over root 2 pi sigma squared e to the power of negative 1 over 2 sigma squared W transpose yi minus W transpose xi squared. And you're still going to do maximum likelihood exactly the same thing, exactly the same way. And if you realize this is still the squared error of the multivariate case, multivariate model, so you're going to get exactly the same results. And so it all checks out. Okay, so it all checks out for the multivariate case as well. Now, you might see the matrix version of this. Okay. Remember, I defined y as the vector of the yi's. Okay, and it turns out that if you have independent one-dimensional Gaussians, this is going to follow a normal distribution with, xw sigma squared I. Okay, now this thing looks kind of scary, but it's just the multivariate version of this case. So think about it like this: in the one-dimensional case, your normal distribution is just this bell-shaped curve, right? But in the imagine you were in 3 dimensions, which is much more realistic, right? Okay, you can imagine like a bell shape, shaped like an actual bell in 3D. So this is just generalizing this idea. Okay, and the probability now, the probability density function, okay, is equal to 2 pi sigma squared minus n over 2. Okay, so this is a slightly different formula because now you have an n-dimensional thing times the exponential of negative 1 over 2 sigma squared. And now instead of the squaring, because we're talking about vectors, we talk about this 2 norm squared. Okay, so in other words, the norm notation here is the same as talking about squared differences when you're talking about one-dimensional things. So with n-dimensional things, you need to look at this kind of thing. Now, hopefully you can see that if I do the minimization argmax for W over probability of y given x, this is going to be the same as taking the argmin of W in this guy, which is exactly the same as the least squares problem that we did, right? That we did in tutorial 1. And so the solution is going to be exactly the same, W hat, x transpose x, inverse x transpose y. Okay. Now the question is, here's our W hat. The question is W hat unbiased? Okay, well, let's check the bias. Okay, how do we take the expectation of this thing? This looks pretty scary. Well, let me just show some rules here. We just said that the expectation of 2z, if z is a random variable, is just equal to 2 times the expectation of z. Okay, well, it turns out that if you have vectors, okay, so if you have vectors, let's say c is a vector, and z is a random vector, so this is a random vector z, constant vector c, you can actually take the expectation inside, okay, because this is exactly the same as the linear property, okay. Let me show you why, okay. What is c? Well, c is just some constant vector c1, let's say to cn, and z is a random vector z1 to zn. So what is ctz? Well, that's equal to c1 z1 plus c2 z2 plus all the way up to cn zn. So when I take the expectation of ctz, I'm taking the expectation of c1 z1 plus the expectation of c2 z2 plus all the way up there. Now, this is just a one-dimensional expectation. We know that this is a constant, so this becomes c1 ez1 plus c2 ez2. And so hopefully you can see that this is just multiplying the constants by the expectation of the elements of z. So this is just c transpose expectation of z. Okay, and that's the reason why we can take it in like this. Okay, why is that important? Well, again, what is the assumption? X is fixed. Okay, so everything out here is just think of this as C transpose. It's just a constant vector, right? It's a vector because X transpose X has dimension n by n. Sorry, X is n by p. So X transpose is p by n. So X transpose X is n by n. Okay, hopefully you remember if the thing on the left is p by n, the thing on the right is n by p. You can only multiply them if their dimension inside is the same. Sorry, and now I just realized my mistake. It's actually p by p. Okay, good that we did that. So this is p by p. Okay, now we're multiplying this, and taking the inverse doesn't change the dimension. So this is still p by p, times X transpose, which is p by n. So p by p times p by n, and y is n by 1. So this vector is p by p times p by n, so it's p by n times 1. And you can think of this guy as a constant. Sorry, I think I said it was a vector, but it's just a constant multiplication of the random vector y. Okay, that was my point. Maybe a long story short. So what I can do is just use the rules and take it all outside of the expectation. Okay, and the expectation of y is, okay, well, let's look back here. The multivariate assumption is this guy, that it's xw. Okay, now hopefully you should notice that this X transpose X multiplied by X transpose X inverse, these guys just cancel out to give you the identity. which is just W. So what does that tell us? Well, that tells us that the bias of W hat is equal to the expectation of W hat minus W, which is equal to 0. So the least squares maximum likelihood estimator, whatever you want to call it in this case, is unbiased, and we can only figure that out once we have this assumption on the y's. Okay? All right, let's do something slightly harder, which is the variance. So let's say we wanted to compute the variance of B hat. I'm going to leave that one to you as an exercise, but you should be able to show that it's actually sigma squared over the sum of xi minus x bar squared. Okay, it's slightly challenging, but I think if you're able to show that, you'll really, I guess it's quite a good exercise just to understand how a lot of the things we're talking about work. But what I want to do is actually cover the harder case, which is the variance of the least squares estimator, the vector form. Okay. Well, before we do that, I just want to refresh you guys on the variance of AZ, where now A is a matrix, constant matrix. So it's just a matrix of constants, no random variables in there. And Z is a random vector, just like we've been dealing with. Okay. Well, the way we do this is just recall in one dimension, what is the variance of 2z if these are just both one-dimensional objects? So 2 is just the number, and z is a one-dimensional random variable. Well, we take the 2 outside and we square it. So 4 squared variance of z. Okay, so you take the constant outside of the variance, but you square it. Well, here you do the same kind of thing, but you can't just square the matrix. What you do is you have A outside times the variance of Z times A transpose. Okay, so this is kind of the multidimensional analog to this rule. Okay, all right, so let's go back to the variance of W. Okay, well, this is the variance of X transpose X inverse X transpose Y. Okay. So let's see here. We can think of this whole thing as our A. I know I called it C before, but we should really call it a capital letter because it's a matrix. And let's use this rule. Well, it's going to be X transpose X inverse X transpose variance of Y times the X transpose X inverse X transpose transpose. Okay, this is our A transpose. Okay, what is the variance of Y? Well, we know that Y is just XW sigma squared I. Right? So the variance is just very simple, sigma squared I. If I plug sigma squared I into here, this is just a number times an identity matrix, so we can just take the sigma squared out the front, and what we're left with is, now what is the transpose of this guy? Well, transpose reverses the order of everything. So this X comes first, and then we transpose it, so we just get an X, and this stays the same. okay? Because, let me just explain it over here, X transpose X inverse transpose is the same as X transpose X transpose inverse. You can actually swap inverse and transpose. Now, X transpose X transpose, well, it's going to swap the order and then transpose. So it's exactly going to be X transpose X inverse. So the value doesn't change at all. Okay? In other words, that tells you that X transpose X is symmetric, right? Because if I transpose it, I get the same value. Anyways, what does this tell us? Well, this X transpose X and this X transpose X inverse cancel out, and we'll just get X transpose X inverse. Now, you should remember from the first video, we actually computed this value for the 2x2 case, right? For the one-dimensional regression. And it should give you, right, if you compute this value again, you should see that you get this thing for the 2x2 element, okay? So in this lecture we showed, or in this video we showed that the expectation of the least squares estimator is the true vector that we're trying to estimate, and the variance is sigma squared over X transpose. Sorry, should not write it like that. Sigma squared X transpose X inverse. Okay, now the last thing I want to talk about before I end is you might think to yourself, you know, I have this estimator for, let me just rub this part out. You might think to yourself, I have this estimator, you know, this is my problem, I have the regression problem, and I've estimated this W, right? And X is fixed because that's just from our data, but what is this guy, sigma squared? Okay, well, sigma squared, remember, is the variance of the error, of the measurement error. Okay, so remember we said the error is epsilon I. This is going to be normal sigma squared. Okay, so how do you estimate this? Okay, well, one easy way to estimate it is to look at, well, once you fit your model, okay, we don't know the true error, but we know the estimated error, EI, the residuals, which is just the true value minus the predicted value. Okay, so if I'm trying to estimate the variance of something, and I have observations of the thing, one possible estimator is the average error. Okay, so we take the I equals 1 to n, yi minus y hat I. This is the true y that we observe. This is the predicted y from our model, and we square it. Okay, and we divide by. We don't divide by n. We divide by n minus p. Okay, and we call this, let's just call it s squared, because s squared is estimating sigma squared. Okay, all right, so this should be pretty simple to understand. We're going to estimate the error of the measurements. Okay, the best estimate for that is the average error we get from fitting our model. The only thing that's kind of confusing is why do we divide by n minus p? Okay, remember this is a multivariate regression with p features. So why do we take 1 over n minus p, not 1 over n? And the answer is very simple. It's because we like things to be unbiased, okay, or it's kind of convenient to have things that are unbiased. So the expectation of S squared is going to be unbiased. It's going to be sigma squared. If I put the n minus p there. If I don't put the n minus p, okay, what happens is that I get a biased estimator for sigma squared. So you can think of the n minus p as a correction, as a bias correction, so that the estimator that we have is actually an unbiased estimator. Okay. All right, so a lot of this stuff really isn't necessary for this course, so don't worry about this if it's, if it's too much math, if it's scaring you. I just think it's, if you're interested in machine learning, data science, it's kind of hard not to know a lot of this stuff. So I just want to try to kind of give you a full picture. And, a lot of the questions that were coming up in the forum seemed a bit confused about a lot of these topics. So I thought this would be a good time to kind of refresh your memory or introduce you to some of these concepts if you haven't seen them before. But as far as trying to do stuff like this on the exam, you don't need to worry about that, okay? Anything on the tutorials is examinable, but anything that any of these extra videos are not, okay? All right, guys, so I'll see you for tutorial 2